Salem. I'm Deputy Vice Chancellor for Academic Affairs, but I'm also the Vice Principal of the University. And I bring, first of all, the apologies of our Vice Chancellor, who would otherwise have been doing this. He is unfortunately, maybe unfortunately, had to attend a meeting with members of the Department of Education. And I'm afraid at this moment that seems to be an important issue. So I'm standing in for him, and it's my duty to bid you a warm welcome to the events this evening. And of course, a particularly warm welcome to Wits University. If you're from outside of our campus, outside of our university. If you're from outside of Johannesburg, a warm welcome to probably the most exciting city in Africa. If you're from Pretoria, we think of Pretoria as a large suburb. Welcome to the city. And as in the case of our guest speaker, since this is the cradle of humankind, welcome home. As I said, it's my pleasure to say a word of welcome to you, but also to just say a word of an expression of appreciation for the very long history of Wits' association with the Bernard Price Lecture, and in particular with the Institution of Electrical Engineers. I am a civil engineer, and
it's okay, we forgive him.
It was Woody Allen who said there is something that is worse than death: spending a night with an insurance salesman. I'm not sure about a gaggle of electrical engineers, but I'm sure we'll cover that over dinner. Our Wits' association with Bernard Price is indeed a very long one. Bernard Price, of course, was himself a member of staff at Wits University. He started a large part of our work in paleoanthropology as well. But importantly, the first of the Bernard Price Memorial Lectures was held in 1931. And I think it's been an unbroken relationship over that period. This evening is a particularly special occasion for the lecture, and that is because the Institute is 100 years old. And that is a special moment. That we've been able to sustain such a relationship over this length of time, over the length of generations, is testament to the seriousness with which Wits takes its relationship with the Institute, and of course the memory of Bernard Price. It's therefore my pleasure to ask the current president of the Institute, Du Toit Grobler, to come and introduce our guest lecture for this evening. Thank you very much.
Thank you very much, Professor Balam. Ladies and gentlemen, it's really a special honor for us as the South African Institute of Electrical Engineers during our centenary year to continue the long relationship with the University of the Witwatersrand. I would like to first of all express a special word of welcome to the Price family, Richard and Jenny Price. Richard is a grandson of the late Professor Dr. Bernard Price. I'm also honored to say that Richard Price is a certificated engineer, so he's one of us. Very welcome to tonight. We take the advantage of the arrangement that the SAIE has a distinguished speaker available that the SAIE can take to their centers that's distributed throughout the country. Tonight, in fact, is the 12th lecture that our honored speaker will present in South Africa on a tour that started on the 14th, and the 30th of September is the final and the highlight of the 2009 Bernard Price Memorial Lecture. We started in Bloemfontein. We then went to Vanderbilt Park for a Wall Triangle, a center of the SAIE. Bloemfontein, we don't have a center. We only have an interest group at this stage. From there on, we moved to Cape Town for the Western Cape Center. Then to George, the Southern Cape Center. Then to Port Elizabeth, the Eastern Cape Centre. Then to East London, no centre yet, but a very energetic, and hopefully we will soon have a centre there in East London. From there on we moved to Durban, where we have the KZN Centre. And last night we were at Mpumalanga, one of our younger centres, where we had the final of the pre-run of the centenary lectures for this year. So tonight we're here, and it's really after an opportunity of giving all our members, or as many of our members that we could get together at the various meetings, the opportunity to listen, certainly to an distinguished lecturer. William A. Groover is the President of Intelligent Robotics Corporation and Professor Emeritus of Engineering Science at the Simon Fraser University in Vancouver, Canada. He received the PhD, the MS Electrical Engineering and the BS Electrical Engineering degrees from the University of Pennsylvania and the DIC in Automatic Control Systems from the Imperial College of Science and Technology in London. His industrial experience includes management and technical leadership positions at GE Factory Automation Products Division in Charlottesville, the GE International Automation Center in Frankfurt, IRT Corporation in San Diego, the Center for Robotics and Manufacturing Systems at the University of Kentucky, and the LTI Robotics Systems, a California-based startup which he co-founded. He has also held engineering and faculty positions at the NASA Marshall Space Flight Center, the DFVLR German Space Research Center, the Technical University of Darmstadt, the US Naval Academy, the University of Kentucky, and the North Carolina State University. He has published 215 technical papers and 3 books on robotics, automation, control, and optimization. His current research emphasizes the development of distributed intelligence technologies and their application to manufacturing, automation, robotic systems, digital services, and energy management systems. Dr. Groover is a fellow of the IEEE and the Engineering Institute. He is currently the senior past president of the IEEE Systems, Man and Cybernetic Society, for which he was president. Vice President of Long Range Planning and Finance, Vice President Publications, Vice President Conferences, and the member of the Board of Governors. He has served as a division director and a member of the IEEE Board of Directors. That is the main IEEE board. Currently, he is also a member of the IEEE MGA board and is an associate editor of the IEEE Transaction on Systems, Man and Cybernetics, and he co-chairs the Society's Technical Committee on Distributed Intelligent Systems. He served as an associate editor for the IEEE Transactions on Control Systems Technology, and he was a founding officer and an ADCOM member of the IEEE Robotics and Automation Society. Ladies and gentlemen, I now call on William A. Groover to present the 58th Burnett Prize Memorial Lecture, and the topic that he will discuss with us is New Technologies of Intelligent Systems for a Global World. Ladies and gentlemen, I give you a most distinguished lecturer, Professor Dr. William Groover.
Well, thank you very much for that kind introduction, Mr. Grobler. I'd also like to express my appreciation to the SAIEE, and also to Wits University for this opportunity to speak with you. Today I've chosen as my title of my presentation a topic which is very close to my interests for many, many years. It's followed me through my career, both in universities, in companies, and in government laboratories. It has to do with what I call intelligence systems, and I entitled it For a Global World because really that's what we have, and intelligence systems are what we need in order to provide conductivity with that global world. I will give an outline here of the topics. I will discuss, first of all, what is an intelligence system, some definitions, some background on structures and technologies, and then the main part of this presentation will deal with applications. And as an engineer, that's usually where I start. I feel that it's important that we start with applications and have that motivate the technologies. A system can be viewed as an assembly or a group of resources and procedures that accomplish specific functions. Specifically, a collection of personnel or people, equipment, and methods that can actually do a task or a set of tasks. Those of you that are electrical engineers and perhaps other branches of engineering are probably familiar with the feedback control system indicated here. This is what's known as a single loop control system in which we have a plant to be controlled. That's typically something like a motor, could be an airplane, it might be a chemical plant, but that's the plant, and it might be described analytically in terms of equations, a model, mathematical model, or the actual plant itself. Then we have a controller which is able to make decisions on the best way to reduce the error between the sensed output and the desired input. And when that error goes to zero, then we're in control. And this is the basis for much of engineering in terms of control systems technology and their applications. Most large systems have many loops. I was in a chemical plant with Mr. Schroble just recently where I was told they have 1,200 loops and they all interact with one another. Now the word intelligent is derived from the Latin word intelligence, meaning insightful or deliberately. It is a system that is able to sense and learn from its environment and then react to generate actions that enable it to reach its objectives. An example of an autonomous system would be a glider, but a better example would be a human being. You're an intelligent system, each of you, because you have the ability to plan and execute your actions without any external intervention from outside. However, when we cooperate with other people in our environment, then we can often do more, and more about that in a minute. Now here's a little animation that I often give to my students, and sometimes when I talk to younger people in high schools. We have an ant, and this is a being with simple intelligence. Goes out, finds food, and when it finds food, it lays a scent, S-C-E-N-T, that is. Sometimes called, technically called a pheromone. And then that scent disappears after a while. The idea is here that that ant provides a means for communication. They don't talk with people, they do it by this pheromone method. And this has actually been cloned, this idea has been abstracted by computer scientists for a number of years in what's called ant communication, where we have little parts of a, let's say, of a program that go out and search, and then when they find something, they leave a trail that for other parts of the program to follow. Roughly, that's it. in my simple-minded explanation. I'm not an expert in ant communication. I use it. I'm really interested in using technologies, and in some cases I do develop them. But this is an amazing being. I was in Kruger Park some years ago, about 10 years ago, on my first trip to South Africa, and I remember seeing an ant hill that was some 10 feet tall, much higher than I am. And then I saw how it was being built. And that's a true case of intelligent beings in nature. So that gets us into the technologies for systems, for intelligent systems. The first three of these are taken from my society that I'm currently past president of. It's called the IEEE Systems, Man, and Cybernetics Society. Like the SAIE, we have a goal of furthering knowledge about the field of engineering, and we do this through publications, conferences, and technical activities. Now, the technical activities are often centered around these three areas of SMC: systems, man, read human, and cybernetics. Systems engineering is a field of engineering that focuses on design analysis and, above all, the management of complex engineering systems. Human-machine systems are those which try to connect the human operator with machines. In the past, that's been done through keyboards, through joysticks, and now we're starting to have ways to do it with things like haptic devices, which look like small robots in a way, and enable you to then take the motion from your hand and relate it to a machine, such as a robot. Now, this is the ultimate goal, so that a human can control a prosthetic arm or possibly his or her own limbs in the event that a medical problem has made it impossible to control it directly. Cybernetics, that is a word that was coined in the 40s by Norbert Wiener when he was working in Boston, I think either at MIT or Lincoln Labs. And the book was called Cybernetics, Control and Communication in the Animal and the Machine. It was derived from the Greek word steersman, and it really deals with both communication and control. It uses feedback, typically, to adapt and steer the entity toward the goal. The main difference, many computer scientists deal with the technologies of cybernetics, and among them are pattern recognition, genetic algorithms, neural networks, fuzzy logic, evolutionary systems. These are all classes of what are known as soft computing among the computer scientists. And these topics I group under cybernetics. However, in many cases, feedback is not the distinguishing factor of these other technologies. Autonomous agents, that's a very important technology of intelligent systems. An agent is an entity, a person, a computer program, actually a computer, or an autonomous device like an airplane. So this is an entity that perceives its environment and takes actions to maximize chances of success. As I just mentioned, we have simple agents such as programs or parts of programs that solve specific problems, like going out on the internet and finding a reference and then bringing it back. No cooperation necessary. The most complex are you and I, we are rational thinking human beings. So we cooperate with other people in order to reach decisions in most cases. Now, the paradigm of intelligent agents became popular in the 90s. However, it's been known since at least the 60s and has been within the field of artificial intelligence. In fact, distributed AI has been used for many years. In 1992 through 2004, it was the focus of a very large research consortium that I joined in '93, known as the Holonic Manufacturing Systems Consortium, sponsored by Rockwell Automation in the States, BHP Billington in Australia, Daimler in Germany, and Fanuc and Toshiba in Japan, among 40 companies, labs, and universities. I joined through my university and also through my company, which is a spin-off from my university lab. Cooperative agent systems. This leads me into the topic of what is a multi-agent system. That is a system composed of agents that cooperate, sometimes called a holonic system, namely a cooperative agent system. And this word holonic actually is something that I've known now for probably 15 years. I ran across it in a book written by Arthur Koestler, a Hungarian in the 60s who actually did a lot of things. And you can go through Amazon and download or actually buy a used version of the book called The Ghost in the Machine. And it's a fascinating description of how people, and particularly people and organizations, can relate. And he coined the word holon, which, or holonic rather, which is a combination, it comes from the Greek. A holon comes from the Greek and means simultaneously a part and a whole, and then holus. Holus is the word that comes from the Greek, and then on, which is like the suffix, proton, neutron, electron, meaning a small part. So this paradigm, this methodology has been embraced by the engineering field, and in 1990 then, together with Japan, the US, and the other countries, formed the Holonic Manufacturing Systems Consortium to not only develop the technologies, but standardize them and to apply them in manufacturing and supply chains. Neural networks, that's an important information processing paradigm that really mimics the way the brain operates. And this was started, it's really been known since the 60s when Marvin Minsky came out with a similar approach, which didn't really catch on until sometime in the mid-'80s when both computer science engineers and people outside of these fields got together in a conference in San Diego, and from then on it's just been exponential growth of neural networks. Basically, it consists of a large number of interconnected processing elements that are analogous to neurons. They can be computers, they can be programs or little parts within a computer, and in some cases they might even interact with people. And these neurons are tied together with weighted connections that are analogous to the synapses. So when I try to remember something, like I often do in these talks, and can't think of it, then all of a sudden a neuron fires, and I'm able to remember. So that enables me as well as computers to learn and model complex relationships. By the way, neural networks have to be trained, and the way you train it is you apply a known input that has a known output, and you do that many times, 1,000, 10,000, 100,000. Of course, computers can do that quickly. And then you, when the time comes to take an unknown input, then we hope that the neural network can generalize and give you the proper output for that unknown input. Fuzzy logic is one that I really like because it's a way of dealing with imprecise information and data. And in fact, problems that have many solutions rather than one. It's basically a technique which is based on degrees of truth rather than crisp numbers, true, false, 24.5 degrees. And what it does is we have words like fuzzy words, that's what Latvisada called them, like big, small, bigger, warm, hot. These are linguistic variables, and they're modeled often, in terms of what are known as membership functions, which have a continuum of values over a range. And using things like if-then statements, rules, basically, then one's able to set up ways for a fuzzy logic system to make a decision and give you an answer with imprecise data. It was developed by Lotfi Zadeh, professor of electrical engineering at the University of California in Berkeley in the 60s. That time he was chair of the department. In fact, he merged the electrical engineering and the computer science department into one, and that became a trend worldwide. So now we'll move into applications of robotics. I'm going to start with, I'll start with robotics, and then I'll go into manufacturing and a few others. Robotics is something I've worked in since the mid-70s when I was an assistant professor at North Carolina State University. And at that time, I was working on more control and mathematical types of controlling robots. Then some years later, about 6 years later, then I started my small company in California, which actually became larger than a small company, and we were then working on systems integration for the installation of robots. But let me give you a little bit of background. What is a robot? First of all, a robot is an electromechanical device. Usually has electric motors. Previously, it had hydraulic motors, and it still has hydraulic actuators for very heavy objects. So that's the robot. Number of geometries. It might look like a human arm. It might look a little different. For example, it might have what's known as a SCARA configuration, which is very good for assembly tasks. Limited range workspace, but it's ideal for assembly. Then there's an action, which is a controller. There's some connection, which is similar to the error device in the previous feedback control system I indicated. And then we have sensors, which perceive what the output is doing and then give input to the intelligent connection. Robotics has evolved over the years, but humans have always wanted to replicate themselves. And so back in the 1200s, there were machines. There were things like the governors for machines, and even the Egyptians had machines many years before. 1500, 1550, robotic hands and sketches at least. I'm not sure if they built them, they probably did. And then in the 1800s, dolls, mechanical dolls. Why do we need robots? Well, they're useful machines for not only industrial robots. Here we see a KUKA robot from Germany, a fabulous robot for spot welding and material handling. And then a number of manufacturing applications in factories, painting, palletizing, lifting heavy objects, putting windshields in cars and applying sealant around the windshields. So it's a whole host of applications. Field robotics. There we have robots which don't look like robots. They're basically carts or cars that don't have an operator, at least not directly. At one time, they were controlled remotely, and now they can be controlled autonomously. But field robotics goes further than that. It goes undersea. You might have space robots, and then we'll have the whole class of spatial applications on the lunar surface, for example. Service robots. Here we see a vacuum cleaner robot that you can go out and buy for $300 US and put it in your house, and it'll clean the floor. And I have a video on that one as well coming up. Medical applications like the Da Vinci robot, wonderful invention or creation of one of the companies that enables you to be able to do a physician to have robot-assisted surgery. We don't want to turn a robot loose on people. There always has to be the physician in place to make sure that things are being done appropriately. But the precision of robotics can exceed that of a human. Precision and repeatability. Personal robotics. We'll see some examples of robotic pets and toys. And then the question is humanoid robots. So in summary, we have three categories: industry in these areas, field in these areas, search and rescue too is one of them. I helped the state police in the US to develop a tracked robot that had treads on it, like a small tank about that high, that went in with a camera to hostage situations and do surveillance in volcanoes. That wasn't the state police in the volcanoes, but service robots, domestic entertainment, rehabilitation. That's where we have robots that help to, there are things like powered or orthotic devices that enable a person to have use of limbs where there might not be enough range of motion because of faults with the muscles. And I mentioned the medical robot. So now service robots. Robots have, in the past, always found applications in the 4D topics: dull, dirty, dangerous, and dumb. Of course, this is a lecture or a talk on intelligent robots, so we'll dismiss the dumb ones. In service robots, here we have a whole host of them, I mentioned security, I mentioned healthcare, entertainment, construction, machines that go out and that move large earth movers that can be autonomously controlled, and then cleaning. Now here's the cleaning robot coming up. There's many applications of personal robots. That has not taken off in terms of a commercial reality, and it's not cost effective in many cases. Perhaps the main exception would be the robotic toy, which is the cat that you can buy for a couple $100s. The rest of these are quite expensive. These robotic dogs, however, they were started by the Sony Corporation, and now they're manufactured by a number of companies in the US, actually in Japan and Korea and China. The next slide deals with dexterous robots, which are also autonomous. There you see a robotic hand, and I built these hands in my research lab at both Simon Fraser University and the University of Kentucky. But that's a hand that has cables, and those cables can pull to cause the finger to move through its range of motions. So it has force sensing. Fingertips can actually sense how hard to grasp. Otherwise, and you can grasp an egg, something really delicate, or something harder and give it more force. Unfortunately, it doesn't have as much force as a human hand, and that is often the problem with these tendon or cable-operated devices. Here's a robot that was also developed at the DLR Institute, and I was a junior engineer back in the 70s at the DLR, and my colleague, Gerhard Hitzinger, who we started at the same time. I left, went back to the US and then Canada. Gerhard then took over a part of the DLR dealing with robotics. At that time, we were doing satellite positioning and vehicle control, space vehicle control. And then the next one is a fully autonomous, lightweight robot made out of composites, and the joints have very precision designed motors in them, DC motors and encoders that provide feedback. There's a camera up here to give stereo vision, has stereo hearing. I don't know if this one can walk. I haven't been over to see this one lately. Okay, let me move to the next one. Now, here we have some topics on human-robot interaction. And I just really point out one of these here, and that has to do with ethical motivations. At one time, there was a resistance from the unions. That was back in the 70s mainly, late 70s and early 80s. And we often found the unions battling with the management in whether or not to install a robot, and sometimes the robots were even damaged. mysteriously. That has changed. And at least in the factories and the industries I've worked with in recent years, actually for the past 15 years, I haven't seen any of that. People have recognized now that robots can actually complement human intelligence. And now we have robots and humans working side by side. Safety is an issue because a large robot can kill somebody if the control system goes haywire. And so it's important to either have separation of the workspace of the robot and the human operator, or special devices like cameras that actually image and take an image of and turn off the robot if there's a dangerous problem occurring, or just mechanical barriers, light curtains, another way to do it. Okay, the next topic is RFID, standing for Radio Frequency Identification. It's a wireless technology that enables you to be able to identify an object uniquely. It uses what's called a tag, and the tag has in the middle a chip. This is the antenna wrapped around it, and that antenna then receives electromagnetic energy from outside, from what's called a reader, and then that antenna has enough energy to turn on that chip, and then the chip says, hello, I'm here, I'm a number, and then it gives out a 96-bit number. 2 to the 96 combinations are possible. And that enables you to identify almost anything in the world, in fact, for many years. So the important components are the tag. They can be as small as a couple millimeters, 3 millimeters in fact, or much larger. And then you put that on a person, on an object, on a forklift, and you could even put it on the floor and then have your reader move on the forklift and look for that tag. So first of all, why do we want to use RFID? Well, it can have very fast scanning rates compared to barcodes. It's wireless. Barcodes, you have to be close to the barcode to read it. It automates processes and therefore streams workflow. It does tasks which were previously impossible. For example, scanning through packaging, ice, snow, and dirt. You'll have to be a little careful about both moisture or water and metal, because if you want to guard against RFID being able to pick up a tag, just encase it in metal. Here's the system operation. As I said, there's a reader and there's a tag, and then there's what's known as a carrier. That's a digital device, so it operates at anywhere from 13.6 megahertz up to 2.4 gigahertz, and then riding on top of that is data. So these are the applications. Employee identification and access control at an airport or in a plant. Airline baggage identification, such as at Hong Kong Airport. For many years, they've been using RFID tags, and when you leave there, you find them attached to your luggage, and I always pull them off. Identification and tracking of vehicles. This is often done with an active tag that has a battery in it, so which increases the range. Passive tags, the ones without batteries, frequently have ranges anywhere from a couple centimeters up to maybe 3, 4, 5 meters, depending on the power of the reader. But the active tags, you can pick them up the length of a soccer field. So here's some applications. Vehicle parts. The company Renault, for a number of years, since 2002, has been putting tags on their major parts like shock absorbers in their cars. And then if the part fails in the field in usage, then the the mechanic takes it out, sends it back to the factory, and now they can determine where the part was made and under what conditions it was made to improve the process. Passports, it's used by the US government in all passports nowadays, with a lot of criticism against that, but it's being extended to other countries, I understand. Library books and magazines, for many years, it's been used there in place of the little magnetic tags that were used previously. I should mention that, let me just turn that off. The topic of, or the usage of these RFID tags has really grown over the past 4 or 5 years due to the efforts of Walmart. Walmart now requires that all of their suppliers put on tags on their cartons. And then when they come in, that tag has information. It usually has this big number, and then that number goes back to a database, which tells you a lot about what's in the carton. Here's the system that we've developed in my company. It basically consists of a computer. You can think of that as a netbook or a small computer. We have a specialized one that we've developed that's fairly small. And then you have the RFID inputs and other sensor inputs like vision, like smoke, and various sensors. And then outputs could be a digital sign, a digital output that gives a visual output, an alarm, or even lock or open a door. Then you put this together in a network, and now you can have an autonomous system which, no matter where you are on this, and these are those little systems on this last slide, and they're wirelessly connected. Now, the nice thing is that if the circuit here is broken because maybe either the computer fails here, or this is on something which takes it out of range, breaks the connection, then another path can be taken. This is what's called a mesh network. It enables you to be able to have at least 2 ways to reach a destination in a wireless network. And that's commonly used now in large cities. Taipei has one. Philadelphia is one among the first. Let's see. Singapore is another city that has mesh network systems. It's only used for communication. It doesn't have the capability here unless you provide a computer at every what's called a node. Now, these mesh networks are used for police and emergency fire communications in the cities. And no matter where these devices, where these vehicles are in the city, they'll have access. You don't have to depend on a cell phone tower. There's no need to have, it's a separate independent network. Here's an example that we've developed for airport queue management as well as fast food and banks. We put RFID readers as strategic points in the queue, and then a person comes in and walks through the queue. Smart home, that's a really important one for RFID as well as other sensors. And it's a little hard to read, but basically you have the whole home outfitted with sensors and beds on people to detect, for example, blood sugar, weight, and blood pressure. Maybe record restless sleeping, snoring, and ECG. Maybe in the furniture to record that somebody's there. And a projection wall to project images of somebody at the front door, or maybe somebody on the other side of the world where you want to talk to them. So it's like a telephone, a visual telephone. So this is the vision of this person that published in this very nice handbook on RFID last year. Human-machine systems. I'll just go quickly through this because basically this is what's used in the smart home, where you put sensors on the body, and that enables you to measure critical aspects. Not only heartbeat or blood pressure, but also limb movement, and what is called here by my Italian friend, shakiness. Fabio Bellafemini, who developed this for Telecom Italia, is a researcher in what's the equivalent of Bell Labs in the States. It's the telecom research part of the Italian telephone company. And this is a product. They use cell phones as a means of getting the information from the body, from the person, back to the physician. And then alarms go off if critical things are exceeded, critical values are exceeded. Brain-machine systems, I promised you something about this. So here's the idea, is to connect that thing to that. And it might be a mechanical hand or it might be something else. So here's the way it's been done in the past. EEG signals have been done with a skull cap that have sensors in them. It's 3 centimeters apart, fairly coarse resolution, doesn't give you a lot of information, I'm told. And by the way, this is the one or 2 or 3 applications that I have not done personally, so it's secondhand information. Next is ECOG. This has to do with using the inner ear and other parts of the body, I believe, to actually measure brain signals. And here you have a much tighter spacing. And then my neurological friends, friends of neurology, I should say, have instrumented animals with their front lobe in order to detect brain patterns. And here a very tight spacing, as little as 2/10 of a millimeter. So here's the brain, some word in Latin there, which I probably can't pronounce. I did have 2 years of Latin at least. And then we have these materials, tungsten electrodes that go into the brain. They're only 0.335 micrometers in diameter, and they're separated here by 500 micrometers. So this is the latest results out of the University of California at Berkeley. So it measures down here the so-called field potential, and then you get the signals, the spikes, and this other signal, which can be used then for the following purposes. They take an animal, put the animal and instrument it with electrodes, and run that into a robot or even a simulation of a robot that is able to do a task. Here the task is to take that yellow circle and match it with the green circle. Now the green circle is moving randomly, and the animal has the chance to move that joystick. A human a physician actually goes and trains, shows the animal how to do that, and then lets the animal do it. And when when he's able to do it, then there's a reward, either a piece of fruit or some reward for accomplishing the task. This is called training, online training. And it was done by my colleagues from the SMC Society, the IEEE, Jose Carmena at the UC Berkeley, and Bob Knight, who's the director of the Institute for Neurology at the university as well. Both Bob and Jose are plenary speakers at our annual conference next month in San Antonio, so I'm looking forward to seeing the latest results. As I mentioned earlier, neural networks, and here you see an example of the neural network that would be used in the modeling and training of this system. It actually wasn't the first time it was done. It was done as early as 2003 by Bob Knight at the UC Berkeley. And talking to my friends in Japan, Toshio Fukuda at the University of Nagoya, he tells me they were implanting electrodes in animals back in as early as the mid-80s. Shared control is the ultimate goal here, and that's so we have a cybernetic man that's able to use thought, brain impulses to control a fully dexterous arm and hand. Hasn't been done, and it's probably going to be a long time before it can be done, experimented at least on humans and implanted in humans. Okay, moving on to manufacturing. I got into this in 1980 when I started my company, LTI Robotic Systems. I actually started the company in the logistics area with my colleague Bob Kennedy from USC, University of Southern California. I left my university position after 4 years and drove with my wife out to California, went thinking I was going to start a company. It turned out I was sitting on top of oil drums, had $5,000 in the bank, and my wife was pregnant on top of that. So it was an exciting time. First year I didn't have any income at all. Second year I was fortunate. I moved part of the company into the area of robotics, and we got a big contract that evolved over a period of 3 years, actually 4 years, from Mitsubishi Electric. And among that successes there, we had up to 30 people working full-time and doing contract work for Mitsubishi Electric on the development of robotics and their applications. Back in 1911, Frederick Taylor wrote a book called The Principles of Scientific Management, in which he said that basically you have to plan everything in advance. Tell the worker what to do, how to do it, when to do it, the time to do it, and that's the way modern management is supposed to be done. Well, forces on manufacturing have caused a lot of changes that are necessary. There's a shortage of skilled and educated workers worldwide. Global markets and manufacturing are causing a demand for higher quality, customization, shorter delivery, and lower prices. There's a lot of barriers in the at least 70s and 80s when I was starting in the area of manufacturing. Islands of automation existed. In other words, you would have work cells that were not really connected in terms of a computer to another work cell, and then you had to have people serve as the interface. That, fortunately, thanks to standardization of these interfaces, is changing the way things are done in companies. Still, there's insufficient reusability of software, particularly of technologies, particularly software. As a result, it still is difficult to change production volume and product design. It's done successfully in painting. However, you have to clean the paint guns at the end of a cycle to remove the colors, flush them out. Spot welding, that's fairly under control. Many tasks are under control, but assembly is the big one. In order to change an assembly workstation, you often have to change the machines that go in there and the feeders. So what are the needs? We need the combination of manual and automated operation, quick installation and startup, the ability to update information quickly, maintain software and develop it easily, and then have flexibility to adapt to changes in the environment. Now here's a project that this is my largest project over the past, maybe 10 years. We had some 15 students, about 5 postdocs, a good dozen professionals from companies working on this. And we started in 2003 and just completed the work this past year. CP Lowen was the company in Winnipeg, and they make windows and doors. The windows, of course, these are the wood frames that go around the windows, and it's called component manufacturing, or the whole process is called a rough mill. Lumber is delivered on large trucks in bundles, and they're actually sorted at the sawmill, and they're cut into boards quite wide, and that's upwards to 20 feet, as little as about 2 feet. And these boards are loaded on a conveyor. They go through a scanner. The scanner adjusts the arbor of the rip saw, which cuts it into strips. And then there's another scanner that adjusts the chop saw to cut it into crosswise. Now, why the scanners? That's because wood is a natural material that has faults, that has splits, it has knots, blue stains, that's on the surface. It could have a number. As I recall it, the standards manual that I worked with had at least a dozen different problems that you have to search for in lumber, and try to eliminate them. And then whatever is left over, you can just send it, chip it out, and use it for pressed wood. And then you sort it, and this is done with again with a vision to sort it into components of certain lengths. Then those components are sent off to the assembly portion of the plant. So we developed for them a multi-agent system, one that assisted the operators to select the best load of lumber, send that information to the forklift, then to cut each piece of lumber into the best combination, and then optimize the schedule. In the past, the scheduling was always done by an operator standing on the floor with a clipboard, and then she would actually take these values down and then determine the schedule on the fly. Now it can be done, at least a decision aid can be given to the scheduler. And then we have a decision support system where an operator was sitting in Vancouver looking at a virtual simulation using the Deneb software to simulate the rough mill. And then the reports were generated based on historical and current information coming from the factory. And there was an intelligent system coordinating all that. This information was, again, used to provide information back to the plant operators that were on the factory floor. Yaskawa Electric, within the Holonik Manufacturing Consortium, they developed a system for assembling highly variable small volume production of AC motors. Small motors about that size. And as you see, they were humans and machines, people and machines operating in a cooperative environment. Similar, but here there were no people. This is too big. Here we have gantry robots that clean this tanker car. The way it does that, there's a hose there that loops around, and then there's a nozzle that forces out under some 100 to 200, actually many hundreds of pounds of pressure, small pellets, which then are an abrasive, which clean the corrosion or the rust off of these tanker cars. 4 gantry robots, 6 axes each, so it was a large coordinated system, and this was done by a Finnish company and a Finnish research lab. At that time, I was the technical leader of the entire consortium. Even though I didn't work on this, I helped to coordinate their activities. And at Daimler-Chrysler, Daimler now, plant in Stuttgart, we worked with them. I did this through my university and my company to come out with an improved way of manufacturing engines. Engines, the crankcase, the shell of the engine was placed on a pallet at this point, and then brought into a workstation where there was a task done, such as inserting bearings for the crankshaft, and then inserting the crankshaft, and then top bearings, and so on. And there were 85 of these actually there was at least 50 workstations along the way, but 85% of the manufacturing was done fully automated with machines. Some of them didn't look like robots, but they were automated. And then at the end, we had people doing wire harness assembly and testing. The problem was some of these machines would jam, and then there would be a backlog where the disturbance would spread out. On this side, you'd have no more parts going down the conveyor, and at this point, it would be jammed. So the solution, the obvious solution, is to take that carrier off, that pallet, and remove it and let the system continue to operate. We did that by having an AGV that was brought in under wireless control, bring out that pallet, take it to a human rework station, and then when the rework was done, bring it back and put it in, and the system keeps on going without losing a beat. Okay, the smart grid. I know a number of you work in the energy area, so you're probably, and I'm sure everybody's familiar, that global climate change is influencing the way we operate. And there's increasing energy demands, quality and reliability of energy is forcing changes. We need active communications where not only can people be consumers of energy, but also suppliers of energy. And what happened is, among other times, this is the big one that I remember recently. In 2003, there was a blackout in the northeast of Canada, actually in the eastern part of Canada and the northeast of the United States. Some 50 million people were without power, trapped in elevators. In fact, 22 nuclear and 80 fossil fuel plants were shut down. It was a serious, many billions of dollars lost as a result of this. Number of people in the Department of Energy and other organizations in Canada, Europe, and other countries got together and formulated white papers. One of these was the smart grid concept. It might be a little hard to read some of these, but for example, if there's a disturbance in the grid, then there would be sensors to detect these problems so that use can be shifted to off-peak times to save money, shut off appliances in response to frequency fluctuations or lack of power, special protection schemes that operate in microseconds to deal with the transients in these electric circuits. And then storage, batteries, both electric batteries as well as fuel cells, which I'll talk about in my next slide, which can also store electricity for later use. And then, of course, you can have energy from small generators, other alternative power sources like micro turbines, and then wind farms and solar. So the smart grid is basically a coordinated intelligent system that one of the key elements of this is a smart meter that senses, collects, and then monitors the data from a consumer. So that now the consumer can go to his or her department store, a hardware store in California, buy a smart meter, buy some software, and buy a solar panel, put it on your roof, and then join the grid. This has been done now for a number of years in California. We're experimenting with it in British Columbia, but in British Columbia, this is what's done. New greenfield or new developments are now being installed with digital meters that have automated monitoring of energy usage, at least 4 times a day or more. Fuel cells, this is basically it's a battery, but it operates on hydrogen, compressed hydrogen. So hydrogen is pumped in, and then hydrogen ions combined with oxygen ions in a proton exchange membrane to produce water and heat. And the output then is electricity, electric current that can operate devices like cars, buses, even stationary fuel cells that can run an apartment building. Here's the basic element of a fuel cell. It's a stack. It's a lot of the cells put together. And then that stack has some plumbing that goes with it that control the air supply, the fuel delivery, cooling and humidification. And this particular one is made by one of my partner companies, Ballard Power Systems in Vancouver, one of the larger fuel cell manufacturers. They're actually located in Vancouver, and they make fuel cells for buses. They also make stationary fuel cells for houses and apartment buildings. Quite expensive. Thousands, tens of thousands, hundreds of thousands of dollars for one of these. And the real problem is you need compressed hydrogen. And to get hydrogen, you have to have them have it made by somebody. More about that in a minute. So fuel cell cars are being built by these companies, and I'm sure there's others coming along the way. And hydrogen fueling stations are needed if you're going to have hydrogen-powered cars. BMW has experimented with that for some time. This is a visualization simulation that we did in my lab for the National Research Council. It shows the tank, and then the compressor, and then actually the fuel delivery, which has a hose then that is attached to a tank in a car. And that car then takes compressed hydrogen, and then there's compressed different banks or tanks of storage that are determined online depending on which one you need. So the real problem with this is you need to have electrolysis or a reformer that generates the hydrogen. So that takes energy, and that's why you see wind farms and electric grid up there. So you don't get anything for free, but at least it can generate hydrogen so that in peak hours you have an alternative power supply. And this is being experimented with at the National Research Council of Canada, where they're also looking at biofuels, methanol, compressed natural gas. And a number of years ago, at least 4 or 5 years ago, it was announced that there would be a hydrogen highway for the Olympics. Now, the Olympics in Vancouver will take place, well, between Whistler and Vancouver, starting in February of next year, just before your big games in the summer for soccer. Now, the hydrogen highway will have running on it a hydrogen-powered buses and vans and fueling stations along the way. And these are in place, they will be operational, and Ford has also provided some hydrogen-powered cars. 7 hydrogen fueling nodes for electrical power generation using renewable power, completely green power. The governor of California, Arnold Schwarzenegger, has announced a couple of years back also that this idea would be extended to California. However, the Canadians thought we were ripped off because it was our idea first. Intelligent communication. Here the idea is to have file sharing. This is my last example of applications. File sharing. Now you can go and buy an Apple iPhone and have file sharing between 2 people. I'm not sure, I don't have an iPhone, so it's possible that you can do it with more than 2 people, but I know you can do it with 2. However, and if I wanted to, I could take this computer right here and hook up what's called an ad hoc network, which is part of the software on there. And that enables you then to go from 1 person to many people in a wireless network within range, that is. What we're doing in my company and a number of other companies, we are coming up with a purely wireless peer-to-peer network that, as long as you're within range of other peers, then anybody becomes a server or a participant in this network and can provide or receive information, and it's bidirectional. It can happen at the same time. You don't have to have a traffic cop telling when this happens. So this is an extension of the idea of wireless ad hoc networks, which have been used for years by the military and others, to commercial wireless networks. And we're developing using FPGA technology, which is a type of computer hardware technology, a chip, which now will take our current circuit board, which is expensive, it's large, 6 inches by 4 inches, uses a lot of power, 7 watts, and then enables that to either come up with a chip or a series of chips that can be put into something like a cell phone and enable pure peer-to-peer connectivity. So the goal is to have integrated digital services where we no longer have proprietary interfaces between all these things, but thanks to Holonic intelligence chips, now we can have strong integration in commercial as well as other applications. So some final comments. As I've indicated, intelligent systems have broad applications to lots of areas, not only robotics and manufacturing, but energy systems, human machine systems, and RFID. They offer, as you saw, reconfigurability, flexibility. I didn't talk much about robustness, but what that means is if you happen to have a machine go down, then if you are in an intelligent environment, then another machine can take up the slack. And so it basically is like fail-safe. Scalability, I didn't talk much about that, but that means that you can start with a small system and scale it up to something larger without having to go in and develop the software from scratch. This depends on what's called distributed intelligence systems, which is topic of a talk that I often give to other groups, and which I actually gave here. Was it here? Yes, it was WITS, to a student group about 2 or 3 weeks ago. And then some other final comments. They've been demonstrated to control physical equipment. We've done that in our Holonic Manufacturing Systems Consortium. Standards are being developed. Among them is the IEC 61149 for the control of PLCs using function block technologies. And now that's has been not only used by Allen Bradley, but other companies worldwide. And as I indicated, new solutions are being developed for integrated digital devices. So I've indicated here a number of sources of information. I'd also like to thank each of these organizations, my company, my lab, the consortium, and then the IEEE, in which now in my new technical committee, we have, there's been an agreement for this consortium to provide all of the intellectual property in terms of reports and IP into this technical committee so our members of that TC can use it. For those of you that would like to learn more about emerging technologies, new ones, look at this, this link. It's the IEEE.org website in which we have an emerging technology page. And that has lots of neat things about wind power and solar power and hydrogen power and so on. And then IEEE TV has a number of videos that you can view, similar to YouTube, but we hope that it's more technical. So with that, thank you very much, and I'd be happy if there's questions to try to entertain them.
Andre Hoffman is a member of the Council of the SAIEE. He's also a past recipient of the Young Achievers Award, and he's serving at the moment as the chairperson of our Technology Leadership Committee of Council. Andre is also in the field of robotics, and he's busy with a colleague setting up a robotic society in South Africa. I would now like to call on Andre to express a word of thanks to Professor Gruber. Andre Hoffman.
Thank you, Troy. Ladies and gentlemen, it's indeed a pleasure for me to be able to propose a vote of thanks to Professor Gruber on behalf of the SAIEE and the Witwatersrand University. When Troy phoned me some weeks ago and said who it was that was coming, of course I was very excited because we are forming the Robotics Association and we're trying to get the energy galvanized, and this was an opportunity for us to have someone in our presence who would be taking a massive road trip around the country, and we really are grateful that someone of this caliber could be here to just share with us his experience. And I've certainly learned a lot of new concepts tonight, holonic systems and various other things which stimulate the thinking. And I was just, one of the questions which came about, which raised for me was, will these intelligent systems ever be able to totally compensate for the non-holonic systems that government puts in place? But I don't think so. But I think the key take home for me here was that ultimately, as Professor said, the applications drive the technology development. And for me, that's what's important. We as engineers have to build a future that we want to live in, and that's the human part. And I think we saw a lot of applications here today that will result in a better humanity. So, Professor, thank you very much. We do appreciate the time that you spent with us. We hope you've enjoyed your stay in South Africa. We hope to see you again.
Thank you.
Thank you.
Thank you very much. It's heavy. The gold bullion?